Have you ever wondered why the ultimate tool for modern automation, a computer script, can completely and catastrophically break over a single misplaced word or even just a missing semicolon? Think about it. When we read a document, our brains are incredibly forgiving. We just use context clues to figure out a typo or a vague sentence and keep right on going. But computers? No way. They are completely unforgiving. A single character out of place and the entire system just jams. Why is that? Welcome to This Explainer. Today, we're on a mission to demystify how computer runtimes handle data and prevent structural errors from bringing the whole shebang down. We're going to dive into the hidden grammatical rules that keep our digital world running smoothly, taking a journey from static text straight into dynamic action.
Here's our roadmap for today. First, static text versus active runtimes. Second, meet the data primitives. Third, typing domains and validation. And finally, preventing structural data errors. Let's jump right in.
Section 1. Static text versus active runtimes, from paper to performance.
To really wrap our heads around computational grammar, we need to adopt what we call a calculus mindset. We're shifting from the traditional drafting of static paper documents to designing dynamic, automated environments. On one hand, you might have a single data entry just sitting inside a static spreadsheet cell. It's totally passive, it's just a mere representation of data. But on the other hand, imagine that exact same entry behaving dynamically inside an active running script. In the active canvas of code, we completely decouple the instructions, the machinery doing the actual work, from the passive raw materials it's processing. The data isn't just sitting there anymore. It's being manipulated, moved, and transformed by the logic of execution.
So, what do we actually mean when we say active? Well, we're talking about the runtime. A runtime is the active execution of programmed instructions from start to finish. You can think of it like a live stage performance of a musical score. You're the composer, right? You design the system, you write the verses and the looping choruses beforehand on your sheet music. But that sheet music isn't the song itself. The song only really happens when you hit play and watch the active stage performance unfold. That live performance, that is the runtime. This all breaks down into a very precise chronological flow. Step 1, you design the instructions. You meticulously plan out the logic and lay down that sheet music. Step 2, you validate the data type. This is basically the rehearsal. You're making sure every instrument is in tune and capable of hitting the right notes before the curtain actually goes up. And then, step 3, you execute the performance. The runtime begins. By isolating the instructions from the data this way, you drastically reduce errors and you can automate some seriously complex performances.
Section 2. Meet the data primitives, the raw materials of code.
If our script is a stage performance, and the variables are the literal notes being played, then we absolutely need to know what those notes are made of. Enter the core data primitives. These are the foundational building blocks in pretty much any script. First up, we have strings. These are simply text characters like the word contract. Second, we have numbers, literally just numeric values, like 500. And third, Booleans. These operate on strict true or false logic. At the end of the day, everything in a computer's runtime essentially boils down to these fundamental types being processed by the instructions you've written.
But to actually work with these primitives, we have to clear a major grammatical hurdle. If you're used to reading English prose, your brain naturally tracks from left to right. To understand code, though, you have to shift your perspective. You need to train your eyes to read variable assignments from right to left. The code takes a piece of data, like a string or a number sitting on the right side of an equal sign, and assigns it to a named variable on the left. It's a totally different way of processing written information, but it is absolutely essential for stepping into that active calculus mindset.
Section 3. Typing domains and validation, the bouncer at the door.
Okay, so now we know our primitives and how to assign them. Next, we have to look at how programming runtimes actually enforce the rules. I want you to think of this mechanism as the strictest bouncer at the door of an exclusive club, making sure everything is completely in check. This bouncer is known as a typing domain. Typing domains are structural rules within a programming language that strictly restrict variables to specific data types. Why do they do this? To ensure they're handled correctly during the runtime. A Boolean, true or false value, simply cannot be processed or treated like a string of text. The computer's machinery is built to do math on numbers, logic on Booleans, and parsing on strings. If the bouncer lets the wrong data type through that door, the machinery literally doesn't know what to do with it.
And this intense strictness brings us to the ultimate linguistic trap. This is especially true for professionals like lawyers, who are amazing at logic but might not be super familiar with programming grammar. Here is the crucial point. Assigning a value uses a single equal sign, but checking or evaluating for equality uses a double equal sign. If you mix those two up, the entire instruction changes. Code doesn't care what you meant to write. It only executes exactly what you did write. It demands incredibly rigid grammatical structures.
This creates a massive contrast between human disciplines and computer science. Think about legal drafting. In law, vagueness and ambiguity are actually often treated as a feature. A human judge can interpret a vague text applying context and intent. But deterministic code? Vagueness is never a feature. It is always a fatal bug. A computer runtime cannot interpret your intent. It relies purely on the unforgiving strictness of deterministic rules and Boolean logic.
Section 4. Preventing structural data errors when the wrong data sneaks in.
Strict validation isn't just some pedantic formatting rule created to annoy programmers. It is an absolute necessity for survival in active digital environments. So pause for a second and think about this. What actually happens when the wrong data type sneaks into a live runtime? What happens if that bouncer looks the other way and a text string tries to sneak into a function designed strictly for a numeric value?
The answer? Deterministic collapse. The runtime instantly breaks. It just shatters. Because the system is completely deterministic, there is zero room for interpretation. When typing domains are violated during active execution, the program doesn't pause and try to guess what you were going for. It just throws a fatal error and stops the performance cold in its tracks. To really visualize this, think of a highly relatable physical analogy. It's exactly like a physical machine sorting blocks. The machine has a square hole designed specifically to process numbers. If you try to force a round peg, say a text string, into that square hole, the machine doesn't just push it through, it jams. The gears grind to an absolute halt. Typing domains exist precisely to prevent that round peg from ever reaching the sorting machine in the first place, ensuring your runtime performs perfectly from start to finish.
So, as we wrap up, let's review the big takeaways from today's explainer. First, shifting to a calculus mindset means understanding that active runtimes decouple static instructions from the active data they process. Second, primitives like strings, numbers, and booleans are the essential raw materials of this environment. Third, typing domains act as that bouncer, strictly validating these materials based on rigid grammatical rules. And finally, this strict validation is the only thing standing between you and a catastrophic deterministic collapse during a live runtime. By understanding these computational rules, you are unlocking an entirely new way of designing logic. So I'll leave you with this final thought. Now that you know exactly how the bouncer works and how the machine processes its raw materials, are you ready to leave the static page behind and begin engineering flawless performances on an active canvas? Thanks so much for joining me today. Keep exploring, keep learning, and I will catch you in the next explainer.